Welcome everyone. We are Team 7172 Technical Difficulties, and we'll be presenting about the Optical Tracking Odometry Sensor, also known as the OTOS. And this is a sensor offered by Sparkfun, and we used it in the past season, and it's given us really amazing results. So we want to share it with you guys. So for introduction, localization is a really key part of what it means to be like developing autonomous sequences. So localization is the ability to be able to pinpoint your robot on the field at any time. So there are many different approaches to this, which we'll talk about on the next slide. But in general, by being able to have your robot position at all times, you can account for differences in field condition. You can account for differences in battery voltage when you're going along your predefined paths. In addition, you can also use corrective algorithms like PID and peer pursuit. So you can up the difficulty of making just from like time-based autonomouses to more complex and just more complex programs in general. So current approaches to localization follow a couple of mainstream kind of ideals. So firstly, we have encoder odometry-based localization. So this was the form of localization that we used before we discovered the OTOS. So this has encoders on each and every drive wheel, and what you can integrate the differences in each wheel to figure out the change in the location of the robot. This is prone to encoder drift because mechanical wheels they have rollers on them, and that means that they are likely to slip. Especially if you're going at speeds like voltages of 1, they become really prone to slippage, and that's not good if you want to have consistent and repeatable autonomous runs. Similarly, you have deadwheel odometry, which includes having 3 odometry pods on perpendicular axes, or 2, and they are used to find differences in each axis of the robot's movement. While these are more consistent than just drive encoders, they are also a lot more expensive with 3 different odometry pods and take a lot more space on your chassis, which reduces the amount of creativity you can put into your robot. You have distance sensors, ultrasonic sensors. So those are just sensors that you use to gauge the distances from the walls. And you also have the Husky lens. So Husky lens is here on our robot. But there's a camera. So the Husky lens is a new AI camera that we use, and we use it to detect pixels over there. We don't use it primarily for localization, but it can be if you have some sort of innovative idea. But we don't recommend it for like hardcore localization because you can only use it in reference to other objects. And we don't have it on the slides here, but we also have a second camera on the back of the robot, which is used for apolitical localization. And that can be used in conjunction with a bunch of other localization techniques. So yeah, next slide. And now this is the Sparkfun odometry sensor, which is just a 1-inch by 1-inch board. It's found right here on the robot, and it's really helpful because it acts like a sort of mouse. It sends a laser down to the bottom of the field and waits for its response, so you can actually track the differences in all different axes. It is featured with a 6-axis IMU, so you can track rotations in all axes, right? So you can. It also gives you heading information. The 3 to 5% error rate means that it's about the same as maybe mechanical drives at a slow speed, while taking up much less space, just one board. And Pierce can tell you about this story.
Yes. So the actual sensor itself has to be located about 10 millimeters above the FTC field tiles, which this makes it so that you don't have much ground clearance similar to odometry, but there's only one pod. You can then like shield it in a TPU mount and then mount it on one side of your robot, allowing for ground clearance on the whole rest of your robot. So it's still much better space-wise than typical deadwheel odometry.
Software-wise, it's also really simple to use. It was recently integrated into the FTC SDK in the new update, meaning that you can just use a simple function call and all the hardware is actually abstracted into the SDK itself. So it requires only minimal tuning. It's 2 scalars, one for the linear motion and one for rotational motion. And that means you can have a fully functioning odometry system in just less than 5 minutes of tuning. There's abstracted hardware calls, which we'll talk about in the next slide, but just one function call can give you the location position of or like the pose of the robot at any time. So you can call it every loop, and it doesn't negatively affect loop times. And there's onboard sensor fusion. There's a microcontroller on the sensor itself, which combines location data from the laser as well as the IMU data, and gives you a completely comprehensive overview of your robot's pose. Yeah. Okay. And then this is the function call. As you can see, it's just a one-liner, and that makes it really, really easy to just slap that in somewhere inside your code, and now you have an odometry system, right? Yeah.
Next slide.
Yes. This is a video demonstration of our sensor in practice. I don't know if you can play it.
Yeah, it doesn't let me play with the.
Okay. Well, you want to see something really cool, but I don't know if you get it. Basically, what we did was it goes up to the board, comes here, hits the wall because we didn't tune it very well. But hey, it works.
It's just a PDF.
And then it goes around and comes back, and we do that like 3 or 4 times just to show consistency. So this is a very, very consistent sensor if you know how to use it properly. So we maintain our velocity so that we don't exceed what the sensor is capable of, as well as we also use April type localization with the camera that we have in front. So every time it hits the back force, it actually delocalizes. Now this might seem like cheating, but we use everything we have available at our hands when we're trying to get the geometry. And if we have such a simple solution, why not use it, right?
Yeah, and for in-person people, I think y'all can probably show them the video after the presentation during lunch or something. So yeah.
So our experiences with the sensor has been wildly successful, right? So our encoder odometry used to be pretty inaccurate. And of course, like, everywhere in the FTC forums, they're like, don't use mechanical encoders, but we wanted to make a smaller chassis, so we have to make some compromises. But now we have this, so we don't really care. So there's a consistent path each front, right? So meaning that you can account for obstacles, you can account for field conditions, battery voltage. If you just have a functioning motion system, odometry becomes a piece of cake. The sensor is actually more accurate at higher speed, which is kind of surprising to us. But so now we can run a robotic one and not have to worry about this. And then we have low ground clearance, of course, and then which may be a bit of a problem for some days, but if you have hardware sort of mitigations or you can count it out with hardware. And it's only $80, which if you consider that the cost of a odometry pod is like $80 per pod, just one of these can fit inside Go Build a Chassis is or Go Build a channel is extremely nice.
All right, so I'm going to talk about our MTI performance. So when using the sensor during MTI in both practice runs and actual matches, it was consistent and it went to like the same point every time. Much better than like what we were previously using with encoder-based odometry. But one main thing about the sensor is that in between each like practice run and actual match, the lens needs
We completely overhauled the navigational system as well. So even with that extra, we had 2 weeks before we had MTI. That's when we decided that we discovered the sensor and we wanted to revamp our entire navigation system. And we made it work. And I don't know if you've seen our autonomous runs at MTI, but they were pretty consistent. And I think that's a hugely in part due to this sensor. And then if you have any questions, you can visit the link, which is the product link for the actual sensor, as well as you can contact us on Instagram. I think we're at FTC7172, or you can send an email to us as well. I think that's everything. So now we're open for questions.
Okay, nice. So for some questions that we have online, how does the sensor affect loop times in auto and teleop?
So the sensor connects to one singular I2C port. So the loop times that we at least saw, our loop times, we didn't work much to optimize them, but even with the unoptimized loop times, it still ran consistently enough that we didn't have to make any massive adjustments to how we were running code bases. So I would say, in our experience at least, it's very minimal loop time changes for a very maximal output.
Okay, nice. And do we have any questions in person? Yeah, you all can.
So when you use this optical sensor, and so your previous experience were with the motor encoders, right?
Correct.
So is there any set of comparison between this and a set of terminals, like even two parallel and even three terminals, and how does it compare?
We personally have not done any testing of that, but from other teams that have tested it, we've seen that the comparison is relatively similar between the two, and that drift is actually marginally less with when using the sensor. So and of course, there's less spacing requirements, so you can make the chassis smaller. So it's more or less the same. Yes.
Do you mind showing the slide of the stuff that the function call parameters that you take in and it passes out again? You guys went through it. It's not.
Oh yeah. Sure. I think it was like 5 slides maybe before.
Okay. Oops.
Exactly.
Which one?
Back to that one. There you go.
Yeah.
Okay, yeah, we have one more question. We'll take from in person and then we will move on to the drawing. So yeah.
Yeah, so for the localization, did you like fuse that with the encoder localizer, like the non-string localizer, or did you just rely on the OTOS?
We relied entirely on the OTOS, but we did also use our equal tags for when we were close to the backboard. So we did have that kind of reset every time we got to us.
Okay, great. Let's give it up for 7172.